As it says on the screen, for the next hour, we're going to be talking about transforming enterprise network connectivity in a cloud-first world, which is a fancy title for saying, what does networking look like for cloud services? And obviously, we've got to focus on Office 365 and Azure and Microsoft connectivity here, but a lot of what we're talking about is relevant for any cloud service you're looking into, how an enterprise network needs to adjust to the way the world works now in terms of cloud services. Quick introduction to myself. I'm Paul Collins. I'm a senior program manager with the Office 365 engineering team, and my role consists of looking after the network performance for the service, ExpressRoute, and so on. And I spend a lot of my time talking to customers, enterprise customers, and helping them do exactly this, transform their network to get the best out of their cloud services. So, without further ado, we'll look at what the actual problem is that we're trying to solve here. So this is a relatively generic diagram, but it may well seem familiar to you in terms of what a traditional enterprise network looks like. They are built with a walled garden, the dotted line here, which is our CorpNet, because inside that walled garden, previously we had our crown jewels, our data, our services, our applications are all hosted within that CorpNet. So we protect that network with anything outside is unknown, untrusted, and therefore we have a very expensive, a very strict security stack to come in and out of that CorpNet. And what that means for my roaming users is that our home office users that are out on a customer site, in a cafe, they use a VPN solution to tunnel into that corporate network to get that data, those services, their applications. And also we use MPLS or other similar network technologies for our branch offices to pull the traffic back to that head office location to go out when we need to. And as I say, anything outside of there is unknown, untrusted. And this model makes perfect sense for that world because that is indeed the case. So a user going to a website goes through traditionally a proxy, SSL break and inspect, DLP, and so on to protect that data, services, applications. But as we move to the cloud world, if we try and overlay the use of cloud services, so we'll start with Office 365 onto this model, it does not work very well. What we're doing is we're lifting that data, service, application up out of that CorpNet and into the cloud. So that model that worked well for unknown, untrusted websites does not scale well for cloud services, as we'll see. And as I say, we'll talk about Office 365 specifically and Azure Connectivity. And we'll also talk about another problem we see with this model, the way that we've had a shift in the update behavior as we move to the new way of working. And as I say, other cloud services, what I'm going to speak about in the next hour is very relevant for any other cloud services you may be working with. So let's walk through those particular elements in a bit more detail. Issues with the traditional model for update traffic. So this is an area I see customers have issues with quite regularly, in that updates have changed. As we've moved to the cloud, updates have become more regular. As we move to an evergreen model of software updates, we used to have a service pack that we'd roll out once every couple of years or so on. Maybe somebody would walk around with a DVD and do that. But now the updates come thick and fast. And if we use that old model, one of the common problems we see is customers with branch offices, for example, pulling updates through that MPLS circuit, utilizing that bandwidth, which is also used for critical business services, to do updates and causing problems. And I asked the Office Pro Plus team what the update cadence was for their services. So the monthly channel, and I'll put that in brackets because it's around 30 a year for the monthly channel. Go figure. But a lot of updates that are around 150 to 200 meg per user if we're just allowing the client to pull that in from the CDN where it's hosted. Even if you're on the semi-annual channel, that's 100 meg for security updates, 350 meg for feature updates. And you start scaling that up to the number of users you have in that bandwidth, that site, we're going to run into bandwidth issues quite often on that MPLS. So that network does not work well for the evergreen model of updates that we see now in the cloud world. Moving on to Azure Connectivity. So we've got two elements to look at here. Connectivity to public IP space, which often, if we don't make any changes, this is going to just behave like normal web traffic because we're talking to a public IP address. So we have issues around latency to the remote site. That service used to sit in that corp net, but now we've put it out in the cloud, so we've got additional physical latency to get out there. And then we've also got the problem of going through that security stack. That security stack adds latency as well. It comes at a tax doing that SSL inspection and so on, in terms of physical cost of the machines to do it, but also a cost of latency. So all this traffic can put quite a high load on that egress because it didn't go through there before, but now we're running business critical services through it, and that can put an enormous load on just from Azure. So the net result, poor performance, poor user experience. Moving on to private IP connectivity. So where we've got an Azure VNet, for example, where we're connecting to private IP space in Azure. Again, latency is still a factor here. We're still going out to an endpoint which used to be sit on premises. So it can also put very high load on that egress as well. So these things start to become cumulative. For running Azure services through there, great deal of load through this egress that wasn't there before. Net result, poor performance. And Office 365 has some pretty particular issues with each service. So I'll start with Exchange Online. And you'll see latency is a key thing throughout this. We want to keep that as low as possible, but it's a key problem we see. So Exchange, again, we're going to run into latency from remote sites that wasn't there before. SSL break and inspect, as I say, adds additional latency. And the other thing to think about here, Exchange Online or Outlook connectivity in the recommended model, i.e. cached mode, works really well at high latency. I've got some customers that are using low Earth orbit satellites to connect to the service at 800 plus milliseconds, and the cached mode functions work pretty well. But there are non-cached operations within Outlook which will be slow if we have network problems getting there, and that means search, opening other people's calendars, free busy lookup, rules and alerts, Exchange Online archive. All these things can be very slow if we have the wrong network connectivity to the service. And one of the other problems that is common, and if you think about this again as a cumulative issue, Outlook, the way that SaaS services work, is different to how that egress was designed. It was designed to protect us from users going to the internet. So those sessions tend to be transient. The user goes to a website, gets the resource, then closes the session so we can reuse the socket, the memory, the processing, whatever else. With things like Outlook, it's going to open multiple TCP sessions to the Exchange service, and they'll sit there all day. So you can see on the little graph there, that's my machine over the course of a day where I had a little gap of working for a nap. And the average of connectivity there is five TCP sessions from my Outlook client to the Exchange service. So you multiply this up by the number of users going through this device, that is an enormous load that was not there before in terms of IP addresses, NATing, processing, memory to deal with that. Those things used to stay on premises. Now they're going through my egress. So cumulatively, we're starting to build up a big problem here. And as I say, these sessions sit there all day and send traffic back and forth. So without very costly upgrades to our egress, the above is very likely to cause issues, and it's something we see very regularly. So that's Exchange Online. When we move on to Skype for Business and Teams, I took to this as a single entity because the problems are the same. Again, latency. We want the latency as low as possible for our real-time media. But one of the key issues you see with that model is the protocol. Skype will work with TCP. Media traffic will work with TCP. But it is not the preferred protocol. It is not the best protocol for audio, video, real-time media. UDP is. So that's what we prefer to use. But when you've got an on-premises proxy, it's very likely that will not support UDP pass-through. We're having to use TCP. And this problem is so bad that if I get an escalation saying Skype is not working for me, or we've got quality issues, my number one question, are you using a proxy? If the answer is yes, pretty much odds on that's going to be the problem. So again, if we think about this again as a cumulative problem, you think of all those Exchange connections, all that Azure traffic, and then we have an all-hands call. This is an enormous building load on that egress that was not there before. And just to show you how easy it is to run into these problems with Skype, this is an output from an online tool we have. It's freely downloadable, the Skype for Business Network Assessment Tool. So I've run it on the left here from my home ISP. So what it does, it replicates a call and it measures the elements the Skype team deem necessary for a high-quality call or meeting. So that's packet loss, latency to the relay server, jitter. So jitter being, for those that don't know, one of the big problems we see with call quality. We want the packets, as I'm speaking, to arrive at the same time so we can be heard and understood. Proxies are pretty common for causing jitter in that the work they're doing is making sure those packets don't arrive in the same order as which they were sent from the client. So they arrive bunched up or spaced out, and that's what causes garbled voice. So we measure that. And packet reorder, where packets are out of order. Again, with UDP, we don't really care too much about this. With TCP, we have to deliver all the packets in turn, so another problem. But you can see here, running from my home network, I've passed all these pretty easily. I hit the relay in 18 milliseconds. Jitter level's pretty low, no packet reorder, which is just as well, because I spend half my life on calls from home. But just to show you what it looks like through a proxy, I have a proxy that sits in Azure in the UK, which I do not use for watching football when I'm abroad. But you can see I forced the traffic through here. So it's using TCP. But this proxy is really well built, so I can stream my football quickly. But it's doing nothing else. It hasn't got your users looking at YouTube videos and all the other stuff they're doing through this proxy. My jitter level is now already above the threshold. You can see it's failed here. It's failed, so I'm going to have call quality through this proxy. So that's how easy it is to run into Skype performance issues through a proxy. So we really need to optimize that audio traffic for Skype to avoid problems. SharePoint and OneDrive for Business. So again, latency is key. And again, I'm talking about cumulative load here. We used to probably have SMB file shares on our network that we use for storage. And now we've said to users, use OneDrive. So these users have put all their years' worth of cat videos in OneDrive and are watching them and streaming them through there. And again, this is an enormous load through that egress that was not there before. So the other problem we see with SharePoint is we use an Anycast system to enable you to reach what we call a front door, close to wherever you egress the traffic. But what it means is we use the same IP address for your tenant, for my tenant, for Microsoft's tenant. It results to the same IP address. So that can make NAT scalability even harder, because we can't use NAT overload to deal with this problem. So the result here, slow file transfer, poor performance of SharePoint and OneDrive. So all these things, we're moving from an on-premises service that generally probably work quite well. And if we have the wrong network connectivity, we can suddenly make this cloud world seem terrible. This used to be much better before we moved to Office 365. And to show you the actual physical impact of that poor network connectivity, we built a demo. So this is a user based in Sydney, Australia, and we've used an MPLS network to backhaul to the USA, to go out to the internet, to Office 365, through that security stack we saw on the first slide. So we're doing DLP, etc., through the egress. So this is a model I see pretty regularly, and one I saw with a customer just a few weeks ago with exactly the problems you're about to see. So here's the client, and as I say, all this network traffic is being taken on the customer's MPLS circuit back to the USA to egress. So to start, what we're going to do is look at latency to the Office 365 front door. So what this means is what the client is talking to connect to the service. So we're doing a PS ping test to outlook.office365.com. So this is going to find what we call a cafe server for Outlook to connect to. And the latency there is 215 milliseconds, which is about right for Australia to the USA. So now we're within Outlook itself, and we're doing search. You won't be able to see that because I can't from here. But it's taking around 320 to 450 milliseconds. And you can see it's clunky. You click on something, it's not instant to respond, but we could probably deal with that. But now we move on to the problems we see the major issues with. Online archive. And you can see there, I'm clicking on something, and it takes a good few seconds before that is there for the user to read and then realize that's not what I wanted, and we have to do it again. Seem familiar to anyone? It's a pretty common complaint here, because this is working real time. There was no cache data here. And here's the big one that you'll get from your exec PAs first, I'm sure. Opening other users' calendars. And you can see I'm clicking furiously on the calendar item there. I'm probably swearing at this point because nothing's happened, but it is. We're going back through this network off to Exchange Online. Finally. Actually not. So we're still waiting for this calendar item to come in. The user's swearing like a trooper, and now Outlook's had a little lie down. And there's no smoke and mirrors here. This is purely a function of the network performing poorly. And finally, there's my calendar item, but that's not the one I wanted. So, dreadful, or your users will use more colorful language, I'm sure. Downloading a simple PPT here. So it's a 15 meg PowerPoint file, and for those that can't see, that's going to be about 5 or 6 minutes. We'd be quicker sending a carrier pigeon for it. An awful user experience from what used to work pretty quickly for this user. So we'll cancel that rather than stand here for 5 minutes. But a terrible, I think you'll agree, user experience. And finally, I'm going to run that network assessment tool. So it's going to check all those elements for me from a Skype perspective. But while that's running, I'll give you an advanced preview of the results. We've failed, unsurprisingly. Packet loss at 4%, so that's way too high. Round trip time, 200 milliseconds. Again, what we'd expect here. And jitter at 63 milliseconds. So this user's audio quality, their meeting quality is going to stink. It's going to be horrible. So all in, this user's experience has gone as well as Brexit. I can say that, I'm British. So what's the solution here? Office 365 connectivity guidance. We've come up with a set of connectivity principles to help guide you in the right direction to solve the problems that cause the behavior you just saw. So I'll run through these quickly and then we'll dig into them in more detail. But we've got 4 principles here. Differentiate traffic. So having a look at the endpoints, and we have to deal with some of them differently to others. This was probably a very tricky thing for you to do previously, but we've done some work recently to make this much easier, which I'll talk about. Egress your connections as close to the user as practical with matching DNS resolution. So that was not happening when you just saw that. We were egressing in the USA, user in Australia. Optimize route length, so avoid network hairpins. So these are things like going in through a VPN concentrator and back out, or pretty much what you just saw again, going through a location to come out again. Get your traffic out directly onto the nearest entry point onto Microsoft's network. And again, I'll explain what that means. And assess network security. So once we've differentiated our traffic, we've identified our core important endpoints, we need to assess, do we need to apply the same security that we apply to a user looking at some dodgy website? And hopefully the answer is no. So let's walk through those. So the differentiation piece used to be very difficult. We used to say just don't proxy Office 365 traffic. But as an organization, your security team will just laugh when you ask them to do that. Because there were thousands of IPs and hundreds of URLs, all with different characteristics. Some are Microsoft owned, live on our infrastructure, some do not. Some are YouTube endpoints, some are Google Analytics. So assessing the risk of bypassing your security stack for that array of endpoints, very difficult. So we've had a very large piece of work happening over the past year or so to consolidate the Office 365 endpoints down to hundreds of IPs, and we're still working on this. They're coming down quite regularly, and the URLs. So to give you an example of how well we've done here, Skype. Does anyone have a guess about how many IP addresses Skype used to have for the audio media traffic? 700, around that mark, a ridiculous number to manage. And recently we've moved that down to two ranges. And what we've also done is mark the endpoints now in one of 3 categories. So this allows you to concentrate on the endpoints that really matter and differentiate them. So we've got 3 categories: optimize, allow, and default. So optimize is the ones we've looked at and said, which ones really warrant that advice? Which ones have massive impact on your performance? Which ones were causing that behavior you saw before? which ones are the high bandwidth, which ones are putting those high load on those proxies, those issues I talked through earlier. And it turns out there are literally 4 URLs and the IP addresses for Skype Media, those 2 IP ranges I mentioned, account for somewhere in the region of 80 to 90% of the volume of traffic to the Office 365 service. These are the high bandwidth, high connection count, latency sensitive endpoints. So if we can concentrate on these, we get an enormous bang for our buck, and it allows your security team to assess the risk of bypassing them. So these endpoints are all Microsoft owned. They live in our infrastructure. We provide IPs for them. We don't expect them to change very often. We very strongly, therefore, recommend SSL break and inspect is not done, proxy bypass is done, local breakout is done, and so on. We'll look what that actually means in a little while. In the middle here, we have the allow bucket. As the name says on the tin, we need those to be accessible for the service to work. So I think ideally we'd say pretty much the same advice here, get them out locally, bypass SSL inspect. But because they're low volume, not necessarily latency sensitive, it's still important these work quickly, but we can treat them differently to the optimized endpoints. We can perhaps put them through an optimized proxy if direct egress isn't possible. And then default is the stuff at the bottom that we don't generally care about, that you could block, but things won't stop working, but the service as a whole won't. So for example, YouTube, used for some help content. You can block that. You'll know if you block that, then this help content won't work, but the service as a whole will work. But the general idea is the default bucket you treat as normal web traffic. SSL break and inspect, send it through a proxy, don't particularly care. And to deliver these endpoints, we've moved away from the old XML file where we used to publish this, which was no longer fit for purpose. And we now publish the information on a web service based on REST API, which allows for automation. And just in the final throes of publishing some scripts on GitHub to query this data, to give you pack files to IP addresses. And we're working with a number of network vendors to automatically pull in this data for you. So you can pull in the IP addresses for the optimized group, for example, into an SD-WAN device. And just for reference, here's what those optimized categories are. I'm not going to read through all that. And by the way, the slides for the sessions, all the sessions are available in the Microsoft Tech community. So if you sign in there, you'll be able to find the slide deck and download it. And as you probably saw at the back, they're recording today, so you should be able to rewatch the recording if you really want. But the optimized categories, as I say, here's Skype. We've got 4 UDP ports now. Another improvement the Skype Teams team have done. We used to require 10,000 UDP ports for Skype Media to work over UDP, which was always a great ask of a customer security team. We've got that down to 4. So 4 UDP ports, 2 IP address ranges that are allocated to Skype for Business, and we're golden. We can do local egress with UDP and using the best connectivity model the service requires. All that traffic, media traffic, is encrypted, so we hopefully can deal with those security questions. And Exchange Online has 2 endpoints, those high volume endpoints you saw before, and SharePoint Online, also OneDrive endpoints here. We can use tenant-specific endpoints to send these direct if you so wish. And just a quick note on the web service, we have 3 elements to it. We have the endpoints, so this lists those endpoints in the detail, whether they're express-routable or not, whether they are optimized, allow, or default, IP addresses, and so on. The version number, so you can pull the version file and say, has this changed? If it has, pull in my changes, again, helping with automation here. And if you're really interested, there's a changes file that will tell you what's changed since the last time. And the other point I'll make here, some of these elements I'm going to talk through relatively quickly to give you the whole scope of what we see as enterprise connectivity. But we talked in detail about a lot of these elements in more detail at Ignite, and there are links at the end of the slide deck for you to dig into those areas if you wish. So I'll talk about these middle 2 as one, because generally they are. And to frame this, we've got something that, for me, is one of Microsoft's biggest unsold assets, we don't talk about it enough. It's one of the largest networks in the world. I believe it's number 2 in terms of the volume of traffic that we take across the world. It's a private network 100,000 plus miles of fiber in 130 locations. So this is Microsoft's global backbone used for Office 365, for Azure, and most importantly, Xbox Live traffic, getting it from the user to where it needs to go on Microsoft's infrastructure as quickly and as efficiently as possible. So one of the key points I always like to point out with connectivity to the service is one of the key worries about the internet and cloud is I'm on the internet for, till I leave, when I leave my site to when it hits the data center. It could not be further from the truth. Microsoft's global network is very, very close to most metropolitan areas in the world. I checked the latency from here on the wireless network. I was on Microsoft's network in 2 milliseconds from here. And that same can be said for many global locations. So this is the infrastructure that we use to get your traffic to where it needs to go. And further, from a Microsoft Office 365 perspective, we're continually moving the edge of the service to the edge of this network. So one of the Ignite sessions that's linked at the end talks in more detail about how Exchange and Skype connect and how we use local front doors to the service. But often, even though my tenant might be located in the USA, I can hit the front of the Exchange service or the SharePoint service or the Skype or Teams service in our Amsterdam data center, regardless of where my tenant lives. And just to show you where the data centers are for Office 365, just so I can make another point, if you set up your tenant in Europe, your data, and this is a key element to think about. In the old world, we build our networks from our clients to our data and services because they're static. With the cloud, your data is not in a place. It is in a region. So your mailbox, for example, if you're in the European region, your mailbox, I often get customers saying to me, my mailbox, my tenant is in Dublin or Amsterdam. Well, it is, but it's also in Dublin. It's also in Helsinki. It's also in Vienna. So the active endpoint at any one time could be any one of those locations. So we don't build networking to where we think our data is because it's distributed. And what we do is build our networking to get onto this network as quickly and as efficiently as possible. And then we can deliver the front door of the service as close as possible to your user. And another point just to make here, announce new data center locations. So if I use South Africa as an example, I've been talking to customers there for many years to say, they ask me, well, we have no data centers in South Africa, my tenant's in Europe, so shall I build a network that egresses in Europe? And the answer has always been no. Egress in South Africa, we can deliver elements of the service without a data center locally in Johannesburg and Cape Town. And we've got data centers opening there very shortly. And what it means is that customers' network does not now need to change. They are abstracted from the change that happens in the cloud with the model that we're talking about. And finally, just to overlay for interest, your Azure regions over the top with red triangles there. So the peering locations are listed here. Again, I'd expect most of you can see that. But you can look at this link here, which is peering DB, and it shows Microsoft's ASN, our network number, which is 8075, and every location around the globe that Microsoft's network has presence. So I've done a little table here, and you can see we have network presence in Amsterdam here. We have it if you've got an office in Sydney, Australia. We have one in New York. We have one in Phoenix. We have one in Slough. Everyone's been there, lovely place. But pretty much anywhere you may have metropolitan offices, locations, Microsoft very likely has a local network edge for the traffic to hit. Right, and just to talk now on this slide around how that local breakout model works, how it improves your connectivity. So we use this model of a US-based customer, Contoso, with an office in San Francisco on the West Coast, and their network egress is at their large office in Orlando, Florida. So we're using the customer's MPLS to come across to Orlando to egress, where we hit the Microsoft network in Miami, Florida, which is the nearest peering point to Orlando, and we hit the service front door, in this case Exchange, in around 65 milliseconds. The service will work over this latency, no problem. It's not too high. And then that service front door will connect to the mailbox store, wherever that user's tenant is around the world. But the bit that we can see to the service front door, 65 milliseconds. But if we do local breakout in San Francisco, we can hit the Microsoft Network Edge in San Jose in California, which will hit, in this example, the service front door for Exchange in Seattle, which might be the nearest one available, which then talks to the mailbox server. In this case, 25 milliseconds. So we've brought the latency right down by doing local egress. But further to that, Microsoft are constantly adding service front doors close to where your users are. So it might be that a service front door opens in San Jose, which we have for OWA, for example, which brings that latency down to 5 milliseconds. Absolutely achievable. I did that this morning from here in Amsterdam. So we've got a difference of 60 milliseconds to the connectivity to the service. We're also not having to do that MPLS backhaul, which will cost money in terms of capacity on that circuit. So there are a lot of benefits from a latency perspective. Further to this, and this is kind of a unknown, kind of unpublished benefit, but if you look at the mailbox store here, in areas where we've got multiple large amounts of data centers, USA, for example, we can notice this user keeps accessing their mailbox from the West Coast. So what we're going to do is shift those 4 copies of their Exchange mailboxes over towards the West Coast. Macro improvements in performance, not to be, nothing you can control or see, but it will happen in the background because this user has correct network connectivity in place. All in, much better user experience than backhauling. And just a minor point on ExpressRoute, we don't recommend ExpressRoute for Office 365. It carries a lot of complexity. And one of the other problems is it kind of brings you back to that hub and spoke model we talked about earlier on, that this consortium might have put an ExpressRoute circuit in Washington, D.C. in their head office. But now we've got MPLS backhaul to Washington and then out the service front door there in 85 milliseconds. So rather than ExpressRoute being a kind of priority, golden bullet for our network problems, it's adding 80 milliseconds to our connectivity compared to just doing local internet egress in California. And finally, assessing network security. So now we've differentiated those endpoints. So let's concentrate on those optimized endpoints. We can now have a discussion with our security team and say, well, we've got a very tightly scoped set of endpoints we want to directly egress and avoid our proxy infrastructure. So Skype for Business Teams, just the UDP media traffic. So it's all TLS encrypted. We can use multi-factor authentication. There is very little benefit in trying to break and inspect this real-time traffic. So hopefully we can just let it go UDP direct. Exchange Online. So we've got 2 URLs there that are used for Exchange Online connectivity. We have Exchange Online protection in place, which does its thing to protect the user, the service. Multi-factor authentication available. Anti-malware is done on the service within AOP. Data loss prevention is possible within the service. We've got ATP if you want to add more protection on top of that. And often these things here that we look at, they're done in the service in the application layer where they don't cause a bottleneck. So we don't need to be replicating them at the network edge because we're treating this traffic the same as we do to a user going to an unknown website. And the same goes for SharePoint Online. Again, we can send our tenant-specific SharePoint and OneDrive traffic out direct if we want. We can send the rest of it. If we want to allow access to other tenants, we can send that via the proxy, do DLP, whatever else. I don't mind, as long as our corporate tenant is optimized. So that's Office 365. Let's have a quick look at Azure connectivity options here over this model. So if you'd have asked me 6 months ago, what are the connectivity models for Azure? I'd have said, well, there are 2, private and public connectivity. Connectivity to private IP space in Azure and connectivity to public IP space in Azure. But at Ignite in September, we announced, or the Azure team announced, Azure Virtual WAN, which I'll talk a little bit about, and there is a link to the full session at the end of the deck. But these 3 elements consist of private connectivity, where we use site-to-site VPNs to connect to our Azure VNets, Azure public connectivity to go to my public IP space, which is more like internet connectivity, and then the Azure Virtual WAN, which I'll describe. So, site-to-site VPN for private connectivity, pretty straightforward. We build a IPsec tunnel to the gateway wherever we've set it up. So in this case, it's into East US and West EU where we might have services. And we essentially treat this tunnel as a part of our backbone network, and we treat the services here as if they're part of our corporate network. Pretty straightforward to do. But if we move on to the internet model here, we have a basic diagram here that's using my branch office to come back through my MPLS to go out through my security stack that we described before, our internet proxy, because we're talking to public IP space here. So if we don't do anything, the default path in many corporate networks is this is internet, this is not internal traffic, it's internet bound, we treat it as internet. The other option is we can use ExpressRoute to build a site-to-site VPN tunnel through ExpressRoute. And just to clarify, I mentioned about ExpressRoute for Office before, not recommended. For Azure is the recommended approach. Much simpler, doesn't carry the problems that we have with Office 365. So just a quick note on what ExpressRoute is. It's simply a routing override for traffic that's going to Azure. It's a tunnel between your network and that backbone you saw before. It does not connect you into a data center. It connects you to the edge of that global backbone wherever you choose to terminate the circuit. So we have ExpressRoute availability here in Amsterdam. So if you build an ExpressRoute circuit, you will be on Microsoft's backbone in Amsterdam. But equally, if you use the internet, you'll be on that same backbone in Amsterdam. So often there's a kind of thought process there that this may not give you benefit in some cases. But the circuit consists of two circuits, a primary and secondary. So we have two routers on either end, which means we can burst over the two links. We can take routers out for maintenance without you noticing, and so on. And they consist of two types of peering. So Microsoft peering is where we connect to that public IP space, Azure IP space, and also Office 365 IP space. And then we've got Azure private peering is where you connect those site-to-site VPNs through the ExpressRoute circuit to an Azure VNet that you control. So it's essentially just a routing path from the edge of your network to the edge of Microsoft's. And just a quick note on, again, there's a session linked at the end which goes in more detail on this if you wish, but the different models we have here for ExpressRoute. We have Cloud Exchange Colo, where you can put devices in the rack in Equinix, for example, run your own circuits in and use their cloud interconnect to connect to Microsoft. We can use point-to-point Ethernet connections or any-to-end IP VPN. So we work with vendors like BT, for example, who can create ExpressRoute and make it part of your MPLS, for example. And at Ignite, we announced ExpressRoute Direct, which is a mechanism to provide 100 gig throughput for those customers who really send a lot of data between Azure and on-premises. So again, there's a session linked at the end that talks about that. But there are different models for ExpressRoute connectivity that we can use to connect to both public IP space in Azure, private IP space in Azure, and if we decide it's the right thing, we've gone through the approval process, then we can use it for Office 365. So here is Azure Virtual WAN, and again, I'm going to just touch on it in the interest in time, just so you know what it is, but there's a full hour session on it linked at the end. But it's essentially a feature that allows you to use that Microsoft's backbone network and our Azure infrastructure to backcall between your branch and Azure and branch-to-branch connectivity. So we use a priority path through Microsoft's backbone to bounce that traffic from a branch office back through to another one. So we're kind of replacing that MPLS network, that hub and spoke model that used to work, with a managed network that has a priority path between those sites. We can have up to 1,000 site-to-site connections per hub. So you set up a hub in a region to kind of be the hub for this traffic. 10,000 point-to-site connections per hub. So we can have our roaming users use this model to connect to on-premises resources, if we so wish. And one of the preview features here is OpenVPN, which can be used in this model, or we can use ExpressRoute. And there's also Office 365 policy, so we can use this to configure our SD-WAN devices at our branch office to send the office traffic direct, which we'll see a little later. So these are all elements that we can use to modernize our network connectivity, but what does it actually look like? How do I implement it? Well, we'll start with that diagram again, and I'll just reset. We've got our branch office here, our router, which connects our MPLS circuit back to our head office. So our internet traffic goes through our stack that we saw before, our proxies and so on, and we have ExpressRoute maybe for Azure. So how do we transform this to solve those problems you saw before? So let's imagine this is Sydney and our US head office for that problem you saw earlier in the video. Well, what we're seeing great success in with customers rolling out is the use of SD-WAN devices to replace that router at the edge of the branch office with an SD-WAN device. It's just a smart router, really. But what it means is I can plug in that MPLS circuit, so we don't have to get rid of that straight away. We can leave it as it is, so we can still continue to do what we want. But what we can do is plug 2 internet circuits in here. So these are much cheaper to purchase than an MPLS circuit, incredibly cheaper. And it means we can have multiple ones here. And what it now means is we can now selectively use this SD-WAN device to say, well, what traffic does not make sense to use this path back hairpin through our head office? So from an Office 365 perspective, we can perhaps use this SD-WAN device to read the REST API service, pull in the IP addresses for that optimized group and say, if you see a connection going to these IP addresses, just bung them out of the internet. And what that means is we can hit the service front door in Sydney rather than backhauling through to the USA and hitting the service front door in the USA, which will give us a great deal of performance improvement. And that can be done for all those optimized endpoints. What it also means, those Windows updates, those Office updates, the Pro Plus updates that used to saturate this MPLS circuit, now send them out locally. Get them off a CDN locally in Sydney, and we solve that problem. We use these cheap internet circuits to do so. And I mentioned earlier, other cloud services. These are pretty extensible. If you know the endpoints, you trust them to go direct, we can just add them to this SD-WAN device to break them out locally and send them on their way. So what all that means, we're getting greater performance on our trusted cloud services going out locally to hit the local infrastructure and reducing the load on our MPLS WAN. And the green lines that just arrived there are what some customers then do as a next step. Well, okay, I'm pretty comfortable with this model. I pretty much run this at home. I have 2 ISPs because I don't trust either of them. And it works pretty well. I've had 100% uptime for us, since my wife last unplugged the router. So what it means is, once you've got trust in this model, you can do this. And I've seen customers do exactly this, remove that expensive MPLS circuit, or what some do is reduce the size of it and therefore the cost. So we just use it for that critical traffic that still makes sense to come back here. But what we can do is build a tunnel through here to come back without the use of an MPLS. But this is where Azure WAN also comes in. We can use a managed route through Azure to do exactly this if you so wish. This works also for Azure. That Azure public IP space, we can send out direct. It hits that Microsoft Global Network locally, and Microsoft does the routing on that managed network that's designed to get the traffic from A to B as quickly as possible. And our Azure private connectivity, we can build site-to-site VPN tunnels to our nearest Azure location through the internet. So again, we're reducing latency for the service to connect by doing it via this model. And it works brilliantly when I'm seeing customers do it. So another model I'm seeing customers use in this space looks like the same diagram. The difference being we've got a cloud-based secure web gateway here, which is a fancy way of saying a cloud proxy. But generally, these devices are a bit more intelligent than a proxy. They're security devices that can do other things than a proxy might do. Partners in this space would be Zscaler, tend to be the market leader, Symantec, Cisco, Umbrella, and so on. So there's a lot of vendors in the market here. But what this does is replace that on-premises proxy infrastructure, that stack we saw before, with a cloud-based solution. So it's elastic. It means that I don't have to buy physical hardware. And what it means is my branch office here in Sydney, if for whatever reason I decide to use this model, I can say, build a GRE tunnel to my nearest cloud-based secure, my nearest proxy, cloud proxy. So hopefully this proxy would be in Sydney, I'm in Sydney, and then that proxy can connect to the Office 365 locally. So again, we have this model in place to allow local breakout for Office, for Azure, for other cloud services, and so on. The other benefit of this model is home users. We know we can get rid of that VPN solution. This solution can be used for home or roaming users. We can still force them through our proxy infrastructure, but deliver that locally without using a VPN concentrator and hairpinning traffic back through head office. Now, I'm aware it's starting to look a bit like a plate of spaghetti here, but the green lines are to indicate Microsoft's best practice in this space. We have no control over how well this solution works for you. To give you an example, one of the key things I would do if you're looking in this space is assess how well your vendor adheres to those principles we saw before. There is no good having this model in place if my office here in Sydney, the nearest cloud proxy that my vendor offers is in Singapore. We've now got high latency to the proxy and then into Microsoft services. So assess very carefully how well they're doing routing onto Microsoft's infrastructure. Do they make it easier for you to turn off the SSL decryption for those optimized endpoints and so on? So from a best practice perspective, we would always say these SD-WAN devices, at least for the optimized group, send them out locally. Just send them to Microsoft, and then we cut out the middleman here. As a customer, though, you may have driving reasons to have this model. You want, let's say, simplicity. You just want this SD-WAN device to build a GRE tunnel to here, bang, we're done. Simple. So that might be a driver, or it might be that we have security mandate, that we have visibility into all traffic coming out of the business. So again, this might achieve that model. But as I say, from a best practice perspective, we'd always say those optimized endpoints are sent direct if possible. And then we can also use that SD-WAN device for Azure Virtual WAN, as I said before. We can just use the site-to-site VPN to build a tunnel there. So we're no longer using that MPLS to connect into Azure Private, and we can talk from our London branch office to our Berlin head office, or vice versa, through Azure Virtual WAN, through this SD-WAN device with local breakout. So, quick summary of what SD-WAN means for us. It allows us to be pretty extensible. It gives us a modern network with high bandwidth internet links that are lower cost than MPLS, and allows us to deliver modern connectivity to cloud services locally. So let me just run through some technical benefits. As I mentioned earlier on, that data, the services, the application, no longer live in that corpnet. It doesn't make sense to have that network model in place. And using the SD-WAN local breakout model allows you to be much more flexible and quicker at delivering those services with efficiency. Central security and egress stacks are very expensive to uplift for cloud services. One customer I spoke to had a quote for $40 million to do that for their infrastructure. We strongly suggested using that model to deliver it much cheaper. Either that or I become the vendor that sells it to them. Cloud security elements, as I say, often replicate what's done at the egress. So assess those optimized endpoints. Are we just duplicating what's already done in the service from a performance perspective, a security expectation? It allows an enterprise to be more agile in an increasingly fast-paced world. This is absolutely true. I've had anecdotes from a number of customers who have implemented this model, and they tell me this model, our CTO says we need to roll out this new cloud service next month, which is not unusual. Previously, we might have had to look at that network model and say, I need $1 million worth of proxy to deal with this extra load. That's going to take 6 months and all this sort of stuff. If we've got bandwidth capacity on this local egress because we've planned for this, we can just say, okay, well, tell us what the endpoints are and we're ready when you are. So the network starts to become a facilitator for the business. It allows it to adapt to a modern, fast-paced, changing world, as opposed to a blocker where the network slows down the pace of progress and change. Consider the shift in software update. As I say, local breakout for updates is a great benefit. And those SD-WAN devices can be centrally managed. So again, you don't need a team of people to manage all those SD-WAN devices at each location. Now, here's the big carrot, cost. We have a lot of customers who have done this. It's very rare to get a customer who will speak about what they've done from a network perspective. But a customer, Kelly Services, they have 10,000 employees, 900 global branches, and they switched to an SD-WAN breakout model. In their instance, they used a cloud security gateway to do it. So that actually carries additional cost to the local breakout model, but it worked for them, it delivered their needs. And they saw a 60% reduction in overall telecom OpEx costs when moving to that. And in most branches, we're able to deliver 10 times the bandwidth. Because they're using a cloud proxy solution, they were then able to allow the branch offices to have just generic internet access from that location rather than backhauling and back out of an on-premises solution. So 10 times the bandwidth for 25% of the cost of their legacy connectivity approach using secure web gateways. And that is a figure I'm seeing pretty consistently. As customers move away from those MPLS circuits or downgrade them, common figures are between 2 and 60% cost savings, but whilst delivering performance benefits, whilst delivering usability benefits, flexibility benefits. So combined, these two things are pretty important, pretty strong carrots for this model. So let's see what actually happens when we implement this. So what we've done here, we have the same setup here, and what we're going to do, we're just doing the ping here just to show you as this changes. This is pinging the service front door. This time we're pinging SharePoint, 200 milliseconds again. But what we're going to do is use a PowerShell script to call the REST API, to pull the optimized endpoint IP addresses in, apply them to my SD-WAN device in Sydney. And what that's going to do is say, as I said earlier, when it responds to one of these IP addresses in the optimized group, send it out direct through my SD-WAN IP internet breakout. Anything else, carry on as normal, send it back through USA. And we can see there, that latency to the service front door has come down to 12 milliseconds. Absolutely achievable. Literally, there's no smoke and mirrors, as I say. We've just switched the routing to go out locally in Sydney. And just to show you, normal traffic still coming back 230 milliseconds to yahoo.com, because we're going through our on-premises proxy in USA. Now that PowerPoint that was terrible before, unusable from a user experience perspective, and look at the difference. Again, all we're doing is routing the SharePoint traffic out locally, and that took 7 seconds. Gone from unusable to great. No, we've got users moaning about this. Then the difference to the usability here is stark, and it's simply a function of the network connectivity that we've changed. So we're going to run that network assessment tool for Skype and leave it running in the background. It takes a little while. It does an 18-second call, by the way, 17-second call. And back into Outlook. So search again. You'll probably see it is snappier. Figures come down to 130 milliseconds for that search, and you can just see the difference in the usability of the service. But here's our calendar item. You can already see it's much quicker. Night and day. From a user perspective, it's gone from being awful to, I'll call it delightful again, use your own word. And from Skype's perspective, everything's green now. Our packet loss is down to very little. Round trip time to the edge, the relay server is 11 milliseconds, and our jitter level's well within what we can cope with for core quality. So this user's experience has gone from Brexit to no Brexit, should we say. Okay, and to help you with this, we've been working on a network partner program where we work with network vendors to help them adhere to those principles, to drive them towards best practice, to make it easier for you to deploy these models in that they can read the REST API service and pull in the IP addresses automatically to remove a lot of manual work that you might have to do. Here are our initial partners who are going through this program. So from an SD-WAN perspective, we have Cisco, VeloCloud, Citrix, and Riverbed. And from a cloud proxy solution, Zscaler are running through that program as well. So what we're doing is helping them to align to those principles that you said before, and help you deploy that model. From an Azure Virtual WAN perspective, here are the partners that are working through that, or have been through that Azure Virtual WAN model. And I have a few minutes left, so I have a little bonus slide deck I wanted to go through. But a quick summary, SaaS is really disrupting network and security. It may seem odd that somebody from Office 365 has this discussion about networking, but Office is quite often the first thing that pushes this door, that forces this problem. But there are many, many things that come behind it. So it's prudent within my team to help customers with best practice in this area, not just for Office, but for their for the cloud-first world, as I say. User experience is starkly different if we have the right network connectivity. You saw that. All we did was switch that optimized group to local egress, and the difference is night and day from a usability experience. And the key to getting this working is your network and security team. They're probably already onto this. They know, every network team I speak to are aware of this model, but it helps to set with them that from an Office, from an Azure, from everything else perspective, we're aligned with this as well, and it works beautifully when correctly implemented. Those are the links for the other sessions at Ignite that I talked about. As I say, you can download the slide deck from the tech community, and I have 5 minutes to show you something else. So for many years, I've had a question from customers, pretty much every customer, and it's this one. It's my most hated question. Well, it was. How much bandwidth do I need for Office 365? I cannot give you an answer to that question, because what's right for one customer in the same vertical is completely wrong for another one. So I can't give you an average for customers using Office 365, because you're going to make quite extensive planning decisions based on that. And I don't want you to spend money on something with a guess. But we've never had a good answer. We used to, say, use the calculators, but this is a terrible way of doing network planning, because one, it's kind of a guess, because you put data into the Exchange bandwidth calculator, and if you put wrong data in, you get wrong data out. But it's also a small piece of the puzzle. When I'm planning, I don't need to look at one thing. I need to look at my entire bandwidth envelope. So these calculators kind of give us an idea, but they're not a good approach. And to be honest, I couldn't be bothered ratifying the new Exchange bandwidth calculator. So we came up with a new solution. Haven't really mentioned this up till now. It's publicly available, though. I'll give you a link in a second. But what it allows us to do is collect actual data from your users or your proxy and then analyze it within Azure. How it works, we install two. I'm going to skim through this pretty quickly. We install two elements on the client machine, which just spits data into Azure Log Analytics. So the network connectivity data that you might see within the resource monitor, the connections that the client's making. We've just pushed that data into Azure, into your Azure Log Analytics workspace, and then we can mine it with Power BI. So let me just show you, in the 2 minutes I've got left, what that looks like. So here is the data in. I've just run a query within Log Analytics to look at. I didn't want to show you my network connectivity, so I've used my colleague Roshan's. But what you can see there is all these TCP connections. The process name here, I'm just looking at Outlook here, but I can do anything. If I know the IP space I'm talking to or the process name, I can do this for that. So all I've done is run a query for all the connections going to Outlook. So now I can see the destination port, protocol used, remote IP, because this is going direct, because obviously Microsoft has the optimal model here. And what it means is I can also, if I zoom out, here we go, zoom back in. Because I can geo-map that IP, I also know which front door I'm hitting with this IP, and bytes sent, bytes received. So I get an immensely accurate amount of data this Outlook client has used over the course of an hour, a day, a month, whatever. So that's what the data looks like raw, but we've also published some example Power BI dashboards for your use. And you can see there we've linked where the connections are going to. So I can see if we're hitting the wrong front door from a region, for example. We can see very accurately the amount of bandwidth used over the course of the day. I can map where those connections are going to. Those are those 4 data centers in Europe I mentioned, which is where the majority of his connections are going to, which means that we're all good. So I can get, I can do this from one user, a group of pilot users, all my users, and I then get a very accurate view of my bandwidth requirements for the service. I think this is going to be most useful during pilot phases to give you a very accurate view of your particular use case. So you can then do planning decisions based on actual data. So that's my Exchange dashboard that we publish. Skype. So one caveat, the published solution doesn't capture UDP yet. We have it coming, you can see because I've done it here, but it's not in the tooling that picks up the traffic yet, but we should be with you very close in the next couple of months. But from Skype and Teams, I can then see how much data I'm using over a call. And this is one of the trickier ones, SharePoint. We can't just look at a process for SharePoint because if I'm opening a PowerPoint file in Outlook or in the browser, it's all coming from OneDrive. But I can't just say, look at the OneDrive sync client, because usage is outside of that. So you can see here, what we've done is write a query that looks at the IP addresses for SharePoint and OneDrive. And now I can see my top processes that are using data from OneDrive from there. So I have 6 seconds left. I'm nothing if not efficient. It's available now. I will welcome your feedback. We're kind of V1 with this. I was practicing my session with my son there, he fell asleep. Freely downloadable from GitHub there. Please give us your feedback through GitHub. Tell us what we're missing, what you'd like improved, dashboards that are missing. But hopefully that helps answer this question so I don't have to roll my eyes every time I get asked it. With that, I'll wrap up. Thank you very much for listening. If you get time at the end of the day, please fill in the feedback on the app. They really do use it to drive the session selection for next year. So if you want more sessions like this, let them know. If you don't, well, maybe not do it. But let us know and we can build a better session. Thank you.